Hello everyone, thanks for coming. Today we're going to do a review of what we have learned in our week 7th class of our numerical analysis. So first we discuss how to carry out the QR decomposition numerically. So this is dependent on repeatedly carrying out the Householder transformation. To be more specific, first we reduce the given matrix A to U, Q prime V, where U and V are orthogonal matrices, and Q prime is a bidiagonal matrix. Then we repeat this process iteratively to get a good approximation. That is to say, we stop when Q prime is close to a diagonal matrix. So we discuss low-rank approximation to an arbitrary matrix. This is dependent on the Eckhart-Yang-Mirsky theorem. That is to say, for any given matrix A, the rank K approximation to the matrix A denoted by AK satisfies the following property. If we are doing the two norms, then A minus AK, the two norm of A minus AK takes its minimum value at sigma k plus 1, where sigma k plus 1 is the k plus 1's singular value of the matrix A. If we are using the Frobenius norm, then the Frobenius norm of A minus AK takes the minimum value, where the minimum value is the square root of the summation sigma I squared, where I ranges from k plus 1 to n. So AK can be taken by the summation of sigma I, Ui, Vi transpose. So here, Ui and Vi are column vectors. So Ui, Vi transpose is a matrix. We next discuss the eigenvalue problem of how to find the largest eigenvalue of a matrix. And then we discuss the power method. So the power method is based on the idea that for any non-zero vector V, if the inner product of V and V1 is not zero, then A times V1 can amplify the magnitude of the first eigenvector. So here V1 is the eigenvector corresponding to lambda 1, where lambda 1 is the eigenvalue of the largest absolute value. So if we take k to be sufficiently large, then A to the power k times V divided by the two norm of AKV will converge to V1, the first eigenvector. So we also define the Rayleigh quotient R of x for our column vector x, which is defined as x transpose AX over x transpose x, to measure how close we are to the first eigenvalue of a matrix. We also discuss the inverse power method. Usually, the inverse power method is much more efficient than the power method. Here, we are trying to solve A minus A alpha I x equals to V. And we take x, the solution x, to be the next V. So in this way, the amplify rate is lambda j minus alpha over lambda 1 minus alpha for any other eigenvalue lambda j. So from this formula, we can see that if alpha is sufficiently close to lambda 1, then we can greatly amplify the first eigenvector. So we renew alpha by the Rayleigh quotient, Vk transpose A Vk over Vk transpose Vk. We also use the Rayleigh quotient to measure how close we are to the first eigenvalue. So this is the inverse power method, and thanks for listening.